Welcome to lecture 3 of your solutions lectures. So in lecture 3 and the last lecture, lecture 4, we're going to look at partitioning. And so we're going to talk a bit more about pKa, and we're going to talk about log P and drug absorption. And that's going to lead us on to Lipinski's rules and then colligative properties at the end. So let's first of all focus on drug absorption. So what must a drug do to be able to be active in the body? So what must it do other than bind at the site of action? Well, if we think about it from the point of view of absorption of the drug from oral delivery, since about 80% of our medicines are provided orally. First of all, we will swallow the medicine, and the tablet will need to disintegrate, and the active ingredient will need to dissolve from the tablet. So it'll need to have solubility to be able to do that. And the active ingredient needs to survive in the range of pHs that it could experience within the gastrointestinal tract. It's got to survive the intestinal bacteria. It's got to be able to cross a membrane, often within the small intestine, to be able to get to the bloodstream. But before it's in active circulation, it has to survive liver metabolism, avoid active transport to bile, avoid excretion by the kidneys, partition into the target organ for action, and avoid partitioning into undesired places. Okay, so there's quite a lot that needs to occur before we're in a position where the active ingredient can bind at the active site. So let's consider what happens to our drug to get to the point where it is able to absorb, so to cross the membrane and get into the bloodstream, so nearer the beginning of that process that was on the previous slide. So first of all, most of the medicines, many of our medicines in fact, as I've mentioned in lecture 1, are weak acids or weak bases. And so this means that they ionize at certain pH, as we showed previously, and so they will be in a charged form and also an uncharged form in solution at certain pHs. And in the charged form, they'll be more soluble, but in the charged form, they'll also be less soluble in oil. So they'll be more soluble in water, but less soluble in oil, which means they will be less lipophilic, which is a term you might like to add to your glossary. And so this would mean that although they'd be very soluble, they might be less likely to be able to cross the membrane where they need to go through a lipophilic area. So let's have a look at the pHs of different areas, different fluids. So you can see the range of pHs that our drug may have to interact with or may have to survive within. So as you can see, there's quite a range of pHs from very low in the stomach, so very acidic conditions in the stomach, through to the blood, which is 7.4, which I think is the most alkali system that we have. So a range of between 1.4 and 7.4. What we need then is to have an understanding of whether our active ingredient will be ionized or unionized, which form they will be in those different pH conditions. So our molecule will have a pKa. So what is pKa? Well, this comes from the ionization constants. So if we look at a weak acid here, a weak acid, we have our acid HA, so hydrogen linked to the acid. And of course, that will be in equilibrium as a weak acid with H plus ions and the negative acids. So if you think about this weak acid is COOH, then once on the left side it's COOH, and on the right side it's H plus and COO minus. Okay, so there's an equilibrium there, and we know that within certain regions, a 4 pH pH region near the pKa, we know that we have this equilibrium present. And the equilibrium can be determined from an equilibrium constant, so that will be a capital Ka for the ionization constant, which is that equilibrium constant there, which will be the concentration of the products over the concentration of the reactants in the way that you've seen before. And we can write a similar thing for a weak base. But in the case of a weak base, when we add the extra hydrogen to one side of this, then it will make our base charge. So if you think of NH3 plus as a moiety on a constituent on a molecule, and that will become an H plus and then NH2 on the other side. And so we have an equilibrium constant for that as well. Now, at the point where these two, where the amount of product and the amount of reactant is the same, the Ka will be 1. The concentration of reactants will equal the concentration of products. Okay, so when an acid or base is 50% ionized, at that point, that will be when the pH equals the pKa. Okay, so I talk about Ka here. pKa is minus log to the base 10 of the Ka, so minus log to the base 10 of these ionization constants. Okay. The equation that we use is the Henderson-Hasselbalch equation, and this allows us to look at the relative ionizations of our weak acid or our weak base at different pHs. So we know that at the pKa, we know that we have a value that we know for our weak acid and weak base, which is based on that equilibrium constant that we can calculate at equilibrium, and that's our pKa. And that'll be unique for each weak acid in each weak base. And the pKa will equal the pH plus the log, and that's log to the base 10, of the unionized form over the ionized form. So the amount of unionized form over the concentration of ionized form for a weak acid. And for a weak base, then that ratio is reversed. Now, as you could see here, if we're at a simplified, if we're at a point where we have an equal amount of unionized and ionized in solution, that will be log to the log 1, and that will simplify the equation so that the pKa equals pH, at which 50% of the drug is ionized. So let's look at an example. Here we have the percent of neutral, so unionized, and the percent of ionized of this molecule against pH. And you can see that the green, the neutral form, the unionized form, goes down with pH, and it crosses the blue, which is the ionized form, which goes up as pH increases. And they cross at the pKa of the molecule, which is 4.1. So at 4.1, you can see that we have 50% ionized and 50% unionized in solution, present in solution here. And you can also see that around about 2 pH units either above or below the pKa, we have this equilibrium present where there is a proportion of unionized and ionized present in solution. But when you go above around about pH of 6.1, then we have the 100% ionized, and we have none of our material unionized at very high pH. Now, I mentioned lipophilicity, or a molecule being lipophilic or not lipophilic earlier, and this is a term, as I said, useful to add to your glossary. So lipophilicity means fat-liking, and it is really the most important physical property of a drug in relation to absorption and its distribution and its potency and its elimination. So lipophilicity is therefore often a very important factor in all of these following processes. And they're important both within the biological system and physicochemical properties that would be important for drug development. So the solubility of the drug will be, lipophilicity will be an important term, absorption, which we'll look at a bit later, how well it can bind to a plasma protein, and many other processes that you can see here where lipophilicity is often considered to be a really important physical property. So to consider the importance of lipophilicity, it is important to understand hydrophobic interactions, or the hydrophobic effect. And this is an entropically driven process. If we try to mix something that is very non-polar with water, we create energetically unfavorable, ordered and more rigid structures in terms of the movement of the hydrophobic moiety and the solvents that surrounds or cages it. And this is what makes it entropy driven. Remember that delta G equals delta H minus T delta S. So the hydrophobic molecules are encouraged to associate with each other in water because of this process. Placing a non-polar surface in water disturbs the network of water's hydrogen bonding. It reduces the ability of water to hydrogen bonding, and it causes reorientation of that network of hydrogen bonds to give fewer but stronger water-water hydrogen bonds close to the non-polar surface, as you can see on the left here. And we call this caging because it leads to a rigid cage where the water molecules are interacting more strongly with each other because they can't interact with that hydrogen, with that hydrophobic moiety. And therefore you have reduced the mobility, the motion, you have reduced the disorder of the solvent significantly by having the presence of that hydrophobic moiety within water. So this has this great orientational ordering, is the reason that we have this lower entropy than you would have in bulk water by the presence of the hydrophobic material. This process drives the hydrophobic material to interact with itself, to find other hydrophobic molecules to interact or to absorb to a surface, or to find ways to reduce its interaction with water molecules. So moving it out of or away from that interaction with the water. And so hydrophobic interactions is driven largely by the impact that the hydrophobic moiety has on the solvent molecules, that pushes the hydrophobic moiety away from that water interaction. So why is this important? we've talked about the fact that a very hydrophobic material will want to interact with itself, won't want to interact with water, and the structuring of water will mean that it's entropically unfavorable for it to do so. And so hydrophobic interactions force the hydrophobic moieties to not want to dissolve and interact with water. So you might think then, for a material to cross a membrane, let's make it fairly hydrophobic, so lipophilic, so that it can cross the membrane, that hydrophobic region within the center of the membrane, that lipid region. However, if it is too water insoluble, so too lipophilic, then it may not be soluble enough in the aqueous environment to have a concentration that's strong, that's high enough to be able to be active. And it might therefore not be able to have the desired effect. So if a compound is too lipophilic, it may be insoluble in the aqueous medium, as I said, and it might bind too strongly to plasma proteins, and therefore the free blood concentration will be too low to produce any effect at all. It won't have the ability to be able to bind to its where it needs to bind to have action. It'll distribute into the lipid bilayers, but that might prevent it from reaching inside cells because it will stay stuck within that lipid region where it prefers to be. Okay, so that might make you think, let's switch things and let's go for things where we can have quite good solubility. However, if the compound is too polar, it may not absorb in the first place because it won't have any membrane solubility. So then it would stay in the area where it is first admitted into the body. So it would then not be able to be active. So it is important that there is some lipophilicity of your potential drug molecule, but that there is also some hydrophilicity, so some ability to dissolve in a polar environment for the drug to be active. So how do we measure this? Well, to measure this, we use log P. Now, we've mentioned P before. That's our partition coefficient that I spoke about when I was talking about thermodynamics in equilibria. So we're going to come back to that concept of equilibrium between an organic and an aqueous phase. So we have partitioning, which is now we're going to call it log P. Now remember that in lecture 1 I talked about partition coefficient, where P was a sort of physical equilibrium constant, and it measures partitioning of, say, our active ingredient between an alcohol, an octanol phase, which we call our fatty phase, our non-aqueous phase, and our aqueous phase. So how well does our material partition between those two phases? And then we said that P, our partitioning coefficient, equals the concentration of the API at equilibrium in the octanol phase over the concentration of our active ingredient in the aqueous phase. And that can give you a huge range of numbers. And so it's easier for us to use log P as our term, to log that term and then to use that term. Okay. So that's the end of this first part of this lecture, so the end of lecture 3, and I'll come back to talk to you a little bit more about log P and the importance of these concepts for drug absorption in the next lecture.